Lecture 10. So let's look at let me just list some of the cryptographic methods we've seen so far. So the first was the simplest, and that was simply a simple substitution of letters. So you pick a key, which is some number K, and in the plain text, replace a letter, whatever letter it is, let's just say L for letter, by the eighth letter in the alphabet after L. So for example, if we pick K equal to 5, then if we take a word like yellow, this is my plain text, this gets converted to what in the ciphertext? So if you go in the alphabet and you go circularly, Y, Z, A, B, C, D. So the fifth letter after Y in the alphabet is D. What's the fifth letter after E? F, G, H, I, J. What's the fifth letter after L? M, N, O, P, Q. And we get another Q. The fifth letter after O, P, Q, R, S, T. The fifth letter after W, X, Y, Z, A, B. So in this very simple substitution crypto system, you pick a key, 5, and then every letter is replaced by the letter that comes alphabetically 5 places later. So this is a very, very simple ciphertext. And there's a way to decipher this statistically because one studies the frequency of letters in the English language. So I think the letter E occurs most often. So if you have a large ciphertext, you look for the letter that occurs most often, assume that's an E, that represents E, that tells you what the key is, and then you can decrypt the message. But this is a classical cryptographic method. Then we saw 3 methods much more sophisticated and much more important. There was the Diffie-Hellman key exchange. So this is a public key exchange system. There was the El-Gamal public key crypto system. And there was the RSA. Public key crypto system. And in an introductory course in cryptography, it's useful to know other crypto systems and how they're analyzed. So I'm going to discuss 2 today. One is the Vigenère cipher. And the other are what are called knapsack problems. Right? So these are the 2 new crypto systems for today. So let's look at the Vigenère system. The Vigenère cipher, it modifies, or it's a modified simple letter substitution. system. Remember, in the letter substitution system, you had a key, a number K, and for any letter L, you go to the letter that comes case places later in the alphabet. Right? In the Vigenère cipher, you do something a little bit more sophisticated. More sophisticated means this was from the Renaissance, from the 17th century. So you pick a word. So instead of picking a number, here the key is a number. For us in the Vigenère system, the key is a word. So the example given in the text, I'm looking now, this begins on page 196. Take the word dog. Now, this is going to be the key. So so we want to encrypt a message. Suppose the message again is the same word, yellow. So this is my plain text. And how am I going to encrypt it? So here is yellow, and under it, I'm going to just write dog, 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 dog. Happens to have 3 happens to divide evenly into 6, but that's just a coincidence. So here's what we do. If you have, so here you want to encrypt a certain letter, L. If under the letter is an A, then L goes to L. You don't change it. If under the letter is a B, L goes to the letter just next after L, which is M. If under the L is a C, you move 2 steps around the alphabet, so L goes to N. If L is D, you go 3 steps around the alphabet, M, N, O. If L were E, you would go 4 steps around the alphabet, M, N, O, P, and so forth. So you have your plain text. Under it, you write over and over again your key word. And under each letter, that tells you how many moves around the alphabet you do to encode the letter. So under the Y is a D. That means 3 steps. Right? A is 0 steps, B is 1, C is 2, D is 3. So X, Y, Z, A, B. So Y goes to B. O, what letter in the alphabet is O? O is the, what is it? The 15th letter in the alphabet. So you want to go 14 letters over. And if you go 14 letters over, I think you get an S. No, that's not right. That's ridiculous. So L, if you move it 4 places over, sorry, Y, if you move it 3 places over, gives you a B. E, if you move it 14 places over, gives you an S. I think that's what I said. G, let's see, A, B, C, D, E, F, G. This is 6 places over. What comes 6 places after L? M, N, O, P, Q, R. Now we're back to the next L. Under the next L is a D, 3 places over. L, M, N, O. O, 14 places over. 14 places over from O turns out to be C. G, again, B, C, D, E, F, G, 6 places. 6 places over from W, X, Y, Z, A, B, C. So now so this is the encrypted, this is the ciphertext. Yellow was the plain text. This is the ciphertext. And you'll notice some interesting features of this. First, in the original word, we had 2 letters, LL, the same. Encrypted, they're not encrypted the same. One is R, one is O. On the other hand, the last 2 letters in the ciphertext are both C's, but the letters they come from aren't the same, they're different. So this is a much more sophisticated cipher than a simple single key substitution, right? This is called the Vigenère text. And it's possible to actually break this code statistically if you have a great deal of text. That's something I don't want to get into now because...
Professor, is this chapter 4?
Yes, this is chapter 4, section 2.
Okay, thank you.
Okay. Chapter 4, section 2. But historically, this is an important cipher, an important crypto system. And it's important that you see it. And if I have time next week, I'll talk about statistical methods to attack it. But for today, I just want to introduce this crypto system. How do you decipher it? This is encryption, right? How do you decrypt? The same way. Here's the word, the ciphertext, D-O-G, D-O-G. So if you know the key word, right? What makes this possible, what is kept secret, is the key word. If you know the key word, you know that the letter B, because it's over a D, to get back to the original text, you go 3 letters backwards. 3 letters backwards from B is Y. O is the 14th. O is the 15th letter in the alphabet. If the letter over the O is an S, you have to go back 14 steps in the alphabet, and that will be E. So you decrypt by essentially the same method you use to encrypt. And what keeps this system secure is only the sender and receiver know the key word. The key word is the crux of this. Anyone who knows the key word can easily decrypt a message. So the key word has to be secret. And if the key word is secret, or if you know the key word, encryption is easy and decryption is easy. In fact, in the text, there's a very nice table which puts everything together easily. Let me just see if I can share the screen with it. So here you see this array of letters, A, B, C up to Z. And if, for example, the first letter in your keyword is D, that means if you're converting from something to D, like here is the letter E, go down to the line that starts with D. So E becomes an H in the encryption. And so this little cyclical set of alphabets, actually it's very pretty. You see, you have A through Z horizontally on the first row, A through Z vertically in the first column, and each row is the whole alphabet starting with whatever is the initial letter in the first column. And this little table allows you to do encryption and decryption very easily. So that's the Vigenère system, and that's something to know. Okay. Now, the mathematically more interesting system is what is called a knapsack crypto system. which is also sometimes called a subset sum crypto system. And it's based on the following idea. Suppose I have a set S. Let me just, let's see, let me give you a page reference for this. I D52 seems to be where this discussion begins. Okay, so this is chapter 6, section 6.2, subset sum problems in knapsack crypto system. Okay, and the idea is the following. Suppose I take a certain set of numbers, M, say, well, I'll use the example in the book. The book makes a mistake, 2, 3, 4, 9, 14, 23. And suppose I take the number 35. So I can write 35 as a sum of different numbers in this set. I think 35 is 23 plus 9, that's 32, plus 3. So S is a sum of distinct elements in this set, a subset sum, right? In general, S is a subset sum of a set M if there is a subset M prime of M such that if I take the sum of the elements in M prime, summation X in M prime X, it's equal to S. Right? So 35 is a subset sum of M. It's the sum of the subset M prime equal to 3, 9, and 23. 3, 9, and 23 is a subset of the set M. And if I add these numbers together, I get 35. So this is an example of a subset sum from this set M. And suppose I want to encode a certain number. I'll forget that, think about that in a second. Suppose I have a certain number. I get the number 35, and I transmit 35, and the person who receives 35 has to write it as a sum of 3 numbers from this set. And somehow that will be how the message is conveyed. So maybe the message you want to send is the number 39, the set 3923. You compute the sum set sum, you send it, and then the person who receives it writes again 35 as 3 plus 9 plus 23 and knows that's the subset you wanted to send. So you can imagine this, it's going to change in a minute, but you can imagine it like this. Suppose you want to send your secret, your plain text is some subprime, some subset M prime of M. So you compute the subset sum S, which is the sum of the numbers in M prime, and you transmit S. The person who receives S figures out how to write S as a subset sum from M and has then recovered 3923. Right? So this is a very, very rough approximation. We're going to separate ourselves from this in a minute of how you might use a subset sum to send a message. Now, of course, there's a problem that it might not be uniquely this set of three numbers that adds up to 35. For example, suppose instead of 35, suppose we took the set 2, 4, and 23. So that's 2, 4, 23. That's contained in M. The subset sum corresponding to this S is 2 plus 4 plus 23. That's 29. So that's the number we send. And the person who receives it wants to find the subset that added up to 29. So one possibility is, of course, 2 plus 4 plus 23 equals 29. But it's also the case that 2 plus 4 plus 9 plus 14 gives you 29. So an error in decryption would be to decipher 29 as the set 2, 4, 9, 14. Okay. So that is kind of a problem. Right. But does everyone understand this notion of a subset sum? So let's take another example. Suppose S is the set 2, 5, 12, 29, 61. And suppose 43, sorry, this is M. This is my set M. Suppose I take the number S equals 43. Can we write 43 as a sum of numbers in this set? If so, tell me what they are. You're only allowed to use a number once, at most once. You can't use a number twice.
Twenty-nine, 12, 5, 2.
Let's see. 29 plus 12 is 41 plus 2 is 43. Yeah, exactly. Is there another way to write 43 as a sum of two numbers in this set?
Twenty-nine, 12, and 2.
Well, that's this. That's what we have here. I asked if there's another way to do it.
Okay.
No, I don't think there is. I think
No.
this is unique.
Yep.
So if I start with this subset M prime consisting of the numbers 2, 12, and 29, and from that I compute the number 43, which I transmit. The only way to write 43 as a subset sum from the set M is 2, 12, and 29. Okay. Now, you might say that's typically not what we want to send subsets of numbers. So there's another way to describe subset sums. So we could do it in the following way. Suppose we let x of I equals 0 or 1. So xi is going to be a binary digit. And consider all the expressions of the form 2x1 plus 5x2 plus 12x3 plus 29x4 plus 61x5. So to every 5 tuple, so this is a binary 5 tuple. So these are all zeros and ones. We associate to this binary, this bit sequence, this number S. So whenever you have this bit sequence, I can add up these numbers. These are either ones or zeros. So this corresponds to a subset sum. This is the sum of all the numbers of the set for which the xi is equal to 1. And then if I transmit S, what I'm in effect transmitting is this binary sequence. So I can translate every binary sequence into a subset sum uniquely. It turns out for this set, I'll explain why later, if a number is a subset sum, it is a unique subset sum. There's no way to write any number as a sum of distinct elements of M in more than one way. So every one of those subset sums corresponds uniquely to a bit sequence, a binary sequence of length 5, and transmitting a subset sum number is exactly the same as transmitting a binary sequence, right? So that brings us exactly to what one does in cryptography. You convert your message to a number. You can write your number as a bit sequence in one way, in one form or other, and you can transmit the bit sequence. And you want to be able to do that securely. Okay. So for example, in this case, with this set, if I take the bit sequence 0, 1, 0, 0, 1, this is my bit sequence. What is the number S that corresponds to this? This is 0, this is 1, this is 0, this is 0, this is 1. So this is 5 plus 61, or 66. So this bit sequence corresponds to 66. Okay.
So we are only going to add the ones, not zeros.
Well, you're computing this number. If the x is 0, 2 times 0 is 0. If the x is 1, 2 times 1 is 1. So you're computing this number.
Right. So only one's place we are adding, like 5 is 1 and 61 is 1. So we just add 5 plus 61.
Exactly.
Okay.
So for this bit sequence, what is the corresponding subset sum?
Five, 12, and 29.
Yeah, it's 0 plus 5 plus 12 plus 29 plus 0. So that's 46. That's the corresponding number. Okay.
Yeah, can you repeat this one? How you got 111?
No, I didn't. It's not how I got it. I gave it. I said, here's the binary sequence. What is the number that corresponds to it? I give you a binary sequence. You give me
Oh,
a
okay.
number. I give you this. You give me 46.
Okay.
Right. If I give you 10101, what number is that?
2 plus 12 plus 61.
All right. And what is that?
74.
75. But you were close.
75.
Okay.
Mhm.
Now, let's think about how hard it might be to encrypt or decrypt this kind of system. So suppose we have a set M, which consists of little n different numbers, M1, M2, M3, M4, up to M sub n. So a subset sum is a number of the form x1 m1 plus x2 m2 plus xn m sub n, the number s of this form, where xi is equal to 0 or 1. Right? So every subset sum can be written in this form. So, or where x1, x2, xn is a binary sequence, a bit sequence of length n. So for every bit sequence of length n, I get a subset sum in this way. How many subset sums S are there? That's exactly the same as asking how many n-bit sequences, as a sequence of n zeros or ones, are there? Right? What is the answer?
Usually subsets are 2 to the power n.
Sorry, it's what?
Usual 2 exponent n.
Exactly, correct. 2 to the n, right?
Yeah.
Because if you had just a one-term bit sequence, x1, there are only two possibilities, 0 or 1. So that's 2 to the first power. If you have x1, x2, what are the possibilities? 0, 0, 0, 1, 1, 0, 1, 1. There are 4 possibilities, or 2 squared. And in general, the number of n-term bit sequences is 2 to the power n. So the number of, now subset sums are not necessarily distinct, but there are at most 2 to the n subset sums. Okay? Any question about that? This is a basic combinatorial fact that whether you do math or computer science, you should understand. Okay, so suppose we have the following. I'm Alice. I want to send a bit sequence to Bob. So I want to send an n. So my plain text, what I'm going to start with, is an n-term bit sequence. I have my set M, right? This is a set M with n different numbers. So from my bit sequence, I take summation x sub I, m sub I. I goes from 1 up to n. That's some number S. That's my ciphertext, let's say. And it's this S that I transmit to Bob. So Bob gets this number S. And let's say all Bob knows is, Bob only knows that S is a subset sum. So Bob must find a bit sequence x1 up to xn such that S is summation x sub I, m sub I goes from 1 up to n, right? So Bob has to decompose S into a sum of elements of my set M, right? How does Bob do that? Well, I don't know. He could just do trial and error, all right? So one possibility certainly is we have our set M consisting of n different numbers. We have a subset sum S, which is some summation xi mi, I equal 1 to n. Bob must find this bit sequence. So if he doesn't know what to do, he can just, Bob could try every n-term bit sequence until he finds the number S, finds the bit sequence that gives the number S, right? So how many trials does he have to make? So Bob tries, there are 2 to the n bit sequences, 2 to the n times. So the length of this calculation is 2 to the n. If you're trying every possible subset sum until you find the number equal, the subset sum equal to S, there are 2 to the n subset sums you can try, right? Like if your sequence M had 3 terms, 2, 7, 31, then what are the possible subset sums? So n is equal to 3, 2 to the n is 2 cubed is 8. So the bit sequences are 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. These are all the possible 3-term bit sequences. This corresponds to what number? 0 times 2, 0 times 7, 0 times 31. That just gives you 0. This sequence corresponds to 0 times 2, 0 times 7, 1 times 31. That gives you 31. This corresponds to 0 times 2, 1 times 7, 0 times 31. That's 7. This corresponds to 0 times 2 plus 1 times 7 plus 1 times 31. That's 38. This corresponds to 1 times 2, 0 times 7, 0 times 31. That's 2. This bit sequence gives you 1 times 2, 0 times 7, 1 times 31. That's 33. 110 gives you 1217031. That's 9. And 111 gives you 1217131. That's equal to 40. So there are 8 different bit sequences, and we have 8 subset sums. So if Alice is sending a 3-term bit sequence, she converts that to a subset sum. It's one of these 8 numbers, and you'll notice they're all different. There's a 1-to-1 correspondence for this set M between the bit sequences and the subset sums. Bob gets some number, one of these numbers. He needs to find the subset sum. If nothing else, he tries. He does the same calculation, all 8 possibilities, until he finds the one that corresponds to the number Alice sent him. So it takes up to 2 to the n tries to decode, decipher, decrypt this subset sum message. Okay. Any questions about this? This is
How he will know that this is 1 to 7, 7 to 31?
how do I know 2731?
Mm-hmm.
This is given. That's not,
Oh, okay.
I mean, I can make up any set. I pick this set. If you don't like this set, take a different set and do this calculation. And you'll still end up with 8 numbers here.
If it is given, then why he is calculating those subsets?
No, so you have to understand what so the idea is Alice wants to send a message to Bob.
Mm-hmm.
So what she wants to send, her ciphertext, is a 3-term bit sequence.
Oh,
Right?
okay.
That's what she wants to send, but she wants to do it secretly.
Oh,
So
okay.
she converts this to a number S by this rule. And she
Okay.
sends Bob the number S, and then Bob has to work backwards and find X1, X2, X3. How does Bob do that? Bob just got S. He needs to find the bit sequence. So he can look at every possible subset sum, and one of these, and only one, will be the number S, and that will tell him the bit sequence, right? This is the bit sequence, X1, X2, X3. And these are the numbers S that you get from them. But to work backwards, Bob calculates every possible subset sum, finds the one that finds the S that Alice sent to him, and recovers the X1, X2, X3. That's,
Oh, okay. So S will be unique, right? Whatever she sent, that will be unique.
well, you want to pick M so it's unique, yes.
Oh, okay.
But how many steps does it take Bob to solve the problem? 2 to the n. So decryption, if you're doing it by exhaustion, requires that Bob do 2 to the n calculations.
But Professor, cannot Eve that intercept that number or that exact text can do the same thing?
Sorry?
Eve, let's say, if she
You are
intercept
100%,
that number.
You are 100% correct. So Eve can do the same thing. So I haven't yet described what additional technique Alice uses so that Eve, who intercepts the message, cannot do exactly what Bob does. But I'm doing this one step at a time. First, I want to, so what I'm explaining Bob is doing, Eve can also do. Right? But this is still how you decrypt the message. So
Oh, okay.
one way is by exhaustion. That is, you try all the 2 to the n possibilities until you win. Okay? Now, 2 to the n is a big number, and there's a way to make it much smaller. And that is by using what's called a collision algorithm. Okay. So one way to solve the problem of finding the bit sequence that produces S is by doing 2 to the n calculations. I'm going to show an algorithm which solves this problem in basically 2 to the n over 2 calculations. So instead of 2 to the n, this is the same as square root of 2 to the n, which is much, much smaller than 2 to the n. So you can reduce the number of calculations as follows. So here's my set M, which consists of n numbers. Okay. So this is roughly n over 2, and so forth. I can divide this set into 2 pieces. Here I have roughly, so let's say M, so if I look at the subscripts, this is the set M sub I, where I is in the set of integers from 1 up to n. So if I take the numbers from 1 up to n, I can divide this into 2 pieces, I1 and I2. So I1 is all of the i's between 1 and n over 2, the first half, and I2 is all of the i's which are bigger than n over 2 and less than or equal to n. So I is I1 union I2, right? All I'm saying is that if I take the set 1, 2, 3, 4, 5, 6, I can divide it into 1, 2, 3, and 4, 5, 6, right? All I'm saying is divide the sum into 2 pieces, like the first half and the second half. And let A sub I be the set of all subset sums where I actually, just I want to use the same notation book. So I, the set from 1 to n, I'm dividing into 2 sets. I'll call them I and j. And I are the numbers up to n over 2, and j are the numbers bigger than n over 2 up to n. And I want AI let me do this on a clean sheet of paper. So everything I said is correct, but I want to make it easier.
Can you do the example first so we'll understand better?
Well, in the example,
Mhm.
M consisted of 3 numbers, M1 equal 2, M2 equals 7, M3 equal 31. So I have, so there are 3 numbers, and I divide it into 2 sets, 2 and 7, and 3. And that's all. So the set, sorry, 1, 2, 3. So the set 1, 2, 3 is the union of the sets 1 and 2, 1, 2, and 3. That's all. Just take the set, divide it into 2 pieces.
Mhm.
So I have M consists of the numbers M1 up to M sub n. I choose a set I contained in the integers from 1 to n over 2, and a set J contained in the integers bigger than n over 2 and less than or equal to n. And A sub I is the subset sum corresponding to this, summation mi, I in capital I. So this is a subset sum chosen from the first half of the numbers in your set. And B sub j is summation j in j, m sub j. So these numbers are from the set m1 up to m n over 2. These numbers are from the set roughly m over 2 plus 1 up to m sub n.
So that AI will go from 1 to suppose n,
No, no.
n over 2.
So, no. So I have n numbers in my
Mhm.
set, labeled from 1 to n.
Mm-hmm.
I choose a set of the indices between 1 and n over 2.
Okay.
Set I of numbers between 1 and n over 2. And for each I in this set, capital I take summation m sub I. So this is a subset sum,
Okay.
but only from the half of the numbers in my original set. J is a set of numbers from n over 2 to n, and I look at the corresponding subset sum. So how many numbers AI are there? It's the number of subsets of this set that I can pick. This set has at most n over 2 numbers. So the number of A sub i's is 2 to the power n over 2.
Yeah, that's why I'm saying the summation sign, the top of the summation sign, do we have to write n over 2?
No, there's no top of the summation sign.
Okay.
It's just this is the notation, I and I.
I
The
belongs
of
to
B
big I.
sub
Okay.
j's is also 2 to the n over 2, because I have n over 2 numbers, and the number of subsets of a set with n over 2 numbers is 2 to the n over 2. So here I do n over 2 calculations. Here I do n over 2 calculations. Then I look at my number. There's a number s that I'm interested in. I look at the number s minus b sub j. So this is again 2 to the n over 2 calculations. I have 2 to the n over 2 numbers bj and 2 to the n over 2 numbers ai. And then I look for a collision. By a collision, I look and see, so find I and j if they exist, such that ai is s minus bj. So I have all
So
of
how do
these
you know?
numbers.
How do you know that identical number is there or not?
Because I know there's going to be an identical number because my number s is a subset sum. So it is a sum of elements of m. So it's a sum of elements in the first half of m plus elements in the second half of m.
Okay.
So there's going to exist some unique I and j where ai is s minus bj.
Okay. Thank you.
So I have to look and see how many collisions, when an element of this set is an element of this set. So I have to look and see for each of these, is it in here or not? And this is also going to be roughly 2 to the n over 2 comparisons. So the total number of calculations is going to be roughly 2 to the n over 2, maybe plus a little bit. But in any case, this is much smaller than 2 to the n. So the point of this exercise is just to show that you can improve brute force calculation significantly by using this simple collision algorithm. It reduces the exponent by half. So instead of 2 to the n calculations, it's 2 to the n over 2 calculations. That's all. This is just a useful piece of mathematics to understand. Okay. Now, as you say, what Bob can do, Eve can do. So there's no security in this system yet. We have to figure out a way to make this method secure. We also want to have a sequence of integers where the subset sums are unique. So one example of a sequence, a kind of sequence with unique subset sums is the following. So this is the definition. A super increasing sequence of positive integers is a sequence V equal, or R equals R1, R2, R3 up to R sub n, such that each term is more than twice the previous term. So Ri plus 1 is greater than or equal to 2R sub I for I between 1 and n minus 1. So every term is at least 2 times the size of the previous one. So the example I gave earlier, 2, 5, 12, 29, 61 is super increasing, because 5 is bigger than 2 times 2, 12 is bigger than 2 times 5, 29 is bigger than 2 times 12, and 61 is bigger than 2 times 29. Okay. So this is an example of a super increasing sequence. And a super increasing sequence has the property that, so if this R1 up to Rn is super increasing, then in fact, for every k, Rk is bigger than the sum of all of the previous terms. So if you look at this, 5 is bigger than 2, 12 is bigger than 2 plus 5, 29 is bigger than 2 plus 5 plus 12, and 61 is bigger than 2 plus 5 plus 12 plus 29. Each term is bigger than the previous terms. Right. So why is that? Well, and you can prove this by induction. For example, for k equal 2, we know R2 is greater than or equal to 2R1, so it's bigger than R1. And R3 is bigger than 2R2, which is R2 plus R2, and R2 is bigger than R1. And R4 is greater than or equal to 2R3, which is R3 plus R3, and R3 is strictly bigger than R2 plus R1. And in general, if this inequality holds for k, then Rk plus 1 is greater than or equal to 2Rk, which is Rk plus Rk, which is greater than Rk, and the other Rk is bigger than all this. So in a super increasing sequence, each term is strictly larger than the sum of all of the previous terms. And if you have a super increasing sequence, there's a simple algorithm to decompose a subset sum. So suppose R, or suppose M, is super increasing. Let S be a subset sum, then how to find the subset? So choose S, choose MK, the largest element in the sequence with M sub K less than S. So M sub K less than or equal to S. So that means S is strictly less than M sub K plus 1. So you have these numbers that are getting bigger and bigger and bigger. M1, M2, M sub K plus 1, and so forth. And choose the largest term less than or equal to S. So M sub K is less than or equal to S. S minus M sub K is greater than or equal to 0. And I claim that S minus M sub K, well, S minus M sub K is less than M sub K plus 1 minus M sub K.
Professor, what page number is this?
This is lemma. This is page 354.
Thank you.
Right. So if we have, and this is in fact proposition 6.5. So if you have a super increasing sequence, there's an algorithm, a fast algorithm to write a subset sum to find the subset which produces the subset sum. So the proof in the text is given in what's sometimes called pseudocode as a computer program, but it's easier just to say what's going on. So we know that mi, 2mi, is less than or equal to mi plus 1 for all I. That's what super increasing means. So we choose the largest number k such that m sub k is less than or equal to s, which means s is less than m sub k plus 1. And I claim that s minus m sub k is in fact less than m sub k. And the proof is that if s minus m sub k is greater than or equal to m sub k, then s is greater than or equal to 2m sub k. Let's see. I'm not saying this is the way I would like. Let me put it, let me do it slightly differently. Suppose S is mi1, mi2, up to mi sub r. So this is a subset sum. I1 less than I2 less than I sub r between 1 and n. So then S, if S is equal to this is less than m sub I sub r plus 1. Because the next term in the sequence of m's is bigger than the sum of all of the previous m's. So S is less than this and greater than or equal to mi sub r. So the number k that we pick, the largest k, such that m sub k less than or equal to s is less than m sub k plus 1, is going to be equal to I sub r. And s minus this m sub I sub r is mi1 up to m sub I r minus 1, which is less than m sub I sub r. So that's what I wanted to say, that s minus this is less than m sub I sub r. So the algorithm is at every step, pick the largest possible m sub I. So I have s is this sum. So the largest m less than or equal to s is the biggest one. And you take s minus that, and the largest element of the set less than or equal to this is the next number. And step by step by step, you will decompose s into a sum of elements of the set m. Right? That is the algorithm that works. Right? Here is perhaps the simplest case. Suppose M is the set 1, 2, 4, 8, 16, 32, 64. So what are the subset sums? It's all sums of powers of 2 up to 2 to the 6th. The subset sums are all the numbers up to 127. So if you take any number up to 127, like suppose I take s equal to 53. I want to write 53 as a sum of elements from the set. The largest power of 2, the largest element of the set, less than or equal to 53, is going to be 32. And s minus 32 is 53 minus 32. That's 21. The largest element of the set, less than or equal to 21, is 16. So s minus 32 minus 16 is 21 minus 16 is 5. The largest element less than or equal to 5 is 4. S minus 32 minus 16 minus 4 is 5 minus 4 is 1. So I get S is 1 plus 4 plus 16 plus 32. That's the unique decomposition of 53 as a sum of distinct elements of this set. So if you have a super increasing sequence, it's easy to decompose a number to discover the subset that produces that number. But as someone pointed out, Eve can do the same thing. So how do we make this an encryption scheme and not just a communication scheme? So here's what we can do. Suppose we have our super increasing sequence R, R1, R2 up to R sub n, super increasing. Then Alice chooses secret integers. So these, she's not going to tell anyone. Alice chooses 2 secret integers, A and B, such that B is bigger than 2 times Rn, the largest element in the set. And the GCD of A and B is 1. Then she creates a new set M, M1, M2, up to M sub n, by defining M sub I, or choosing M sub I, congruent to A, R sub I, mod B. So you take a large number B, a number A relatively prime to B, multiply everything in your original sequence by A and reduce it mod B. Right? And this is the public key. So Alice makes public the sequence M. Okay. What does Bob do? Bob encrypts a message X so X is a binary vector. So this is an n-term bit sequence, a binary vector. He encrypts this message as S equal, I can write as X dot M if you know vectors, but this is summation Xi M sub I goes from 1 up to N. So Bob takes his bit sequence and computes the corresponding subset sum from this public sequence, this public set M. And he transmits this back, sends to Alice. So Alice gets this number S, which is summation Xi Mi. I goes from 1 up to N. And how does she decipher this? Compute the number S prime. See, A is prime to B, so A has an inverse mod B. So Alice computes A inverse S mod B. What is A inverse S? A inverse S is A inverse summation X sub I M sub I goes from 1 up to N, mod B. But this is summation I goes from 1 up to N, X sub I. M sub I was A R sub I. And we're multiplying that by A inverse. So the A inverse and A cancel. This is summation X sub I R sub I mod B. So this number that Alice gets by deciphering is a subset sum from the super increasing sequence of R's, and that is easy from this to recover the X sub I's. Right? And in order to do the decryption, you need to know these secret numbers A and B. And only Alice knows this. Bob doesn't know it. Eve doesn't know it. So that's this encryption scheme. So this is really very important from the point of view of cryptography and mathematics. So let me just emphasize, this is section 6.2, which will be the next homework. Homework will come from that.
Professor, in the syllabus, there is no chapter 6.
Sorry?
In the syllabus, it says sections 5.1 to 5.4, not 6.
Correct. So I'm changing it because chapter 5 is much, much more complicated. And there's no
Right.
way that I can go over that material in the
Short period
small
of
amount
time.
time that we have.
Mhm.
So this is replacing the elliptic curve cryptography.
Okay,
And
great.
That requires a lot more mathematics.
And chapter 4 we are going to do or skip?
we're skipping it. We're going directly from RSA to the knapsack problems.
Okay, great. So
Right.
no chapter 4 and 5.
Oh. The only thing we did in chapter 4 is the Visionaire scheme with the alphabet that I talked about at the beginning of this lecture.
Okay,
So that is covered, but nothing else from chapter 4.
okay.
Right.
Thank you.
Okay.
Professor, can you also like update the homework schedule?
Yeah, I'll do that within the next hour.
Okay.
Homework schedule and the reading schedule, please, so that we don't get confused.
Well, the reading schedule follows the homework schedule.
Yeah, but the one you're talking about is not even there. 6.2.
Well, it will be, I say, in an hour. Be
Okay.
patient.
Thank you, Boris.
Okay. So,
Can you give us like final review much ahead so we can prepare?
well, over the weekend I will, yes.
Okay, great. Thank you.
Okay. Yeah. The homework for Saturday will be from chapters 4 and 6.
Okay.
Okay. That is all for today.
Thank
7
you so
o'clock
much.
tonight, I'm online as usual.
Thank you.
11 o'clock tomorrow.
Thank you.
Bye.